We'll continue with optimization now. So everyone likes optimization, right? Because it's mathematics. So what do you optimize usually? Have you done optimization in your courses before? So you usually have a model to predict something or that outputs you something, and you want to optimize for your model so that you have least error in your output, right? That's the optimization. So a model could be a deep network, or could be a normal neural network, or could be anything. The point you want to look at is that we want to look here is how do you optimize. So we just want to go into the basics of how and what we optimize to get the best model. So usually we optimize, we want to minimize errors. So you have a model that predicts something, and you have training labels, right? For example, in some cases you have training labels, so you want to minimize the error between your predicted label and your training label in a deep network. That could be one case. And you estimate the parameter value so that the error is the least. So another thing we already looked at is linear regression. So you already did linear regression, right? We already did it twice. Once in linear algebra and once in probability. And now we also have linear regression here. So if you wanted to fit these data points with a line, what would be the best way? Least square, that could be one, yeah. Least square regression. So let's say you have let's do some exercise. You have, your points are x, y, and you want to fit a line. And you have, so let's put xi, yi, because you have, these are data points. So what is your model? Y, anyone? Ax, plus b. This looks like a line, right? Yes. So this is what we want to fit. So can you formulate a least square problem from there? So can anyone tell me what are the variables you have to optimize? Yeah, and b, right? Yeah. I was just trying to confuse you by putting x and y here. So you have your A matrix will be so first let's put this AXI plus B equal to YI. Then you have XI1 AB. So this is your equation. Let's call it L. So can you tell me what we are minimizing here? You call it least squares. So least squares of what? So the residual, right? So the difference between the two sides of the equation. Or so this. So this is least squares optimization. The difference between other optimizations and least square optimizations is you have a very nice closed form solution, right? You can just express it with the formula and get the solution. So this is the solution to that. And let's say, so you minimize for the model. You sum all the model prediction minus the data point square. So there's a square missing. So these are the errors you are minimizing. The vertical distance is the error from the predicted line point. So the line is the predicted point, and the data point is the red one. So something like this. So we already wrote the equations. So this is a real example of some data in the internet about countries regarding population density. So y-axis is the population density, and x is the land productivity. So log of land productivity. And somehow this seems to be obeying linear relation, almost. So you want to fit a line. Why would you want to fit a line here? So one reason would be to analyze, right? It helps you analyze. Is it away from prediction? What does it mean it's away from prediction? It means that it's different for some reason. So if you see like Nepal is somewhere up above here. So Japan is also very densely populated, even higher population density. So the model says you can cluster, or you can put the countries apart in terms of this output of the model, how the country is, or how the population density is. So the least square fitting is not just for line. You can do it for any hyperplane, any plane. So for example, if you have plane, the equation is ax plus by plus cz plus d equal to 0. So you can do least square. So if it's a more n-dimensional thing, then we call it hyperplane. And that's the same. What about sphere? Yeah. But how can you do that with linear regression? So this is only for linear model, right? You have to do something smarter for other things. So last time we were fitting fundamental metrics, and this is also a 9-variable linear system. And we said that, so I think in the lab we did ax equal to 0 solution. So we found the solution for the fundamental matrix, or the essential matrix, by solving ax equal to 0. If you want to do it by solving ax equal to b, then you just have to put the last element as 1. Because for us, for the fundamental matrix, the scale is irrelevant. Any scale is good for us. It will still satisfy the equations. So here, can I have a volunteer who will formulate the equation? So anyway, yeah, this will be a lab exercise. So we can do it in the lab too. how did we fix scale in SVD when we solved with AX equal to 0? Did anybody do it? Not yet? So you just have to remember that the solution you get from SVD are always unit vector, unit orthogonal vector. The vectors in V are unit orthogonal vectors, right? So the scale is always unit. So you don't have to fix scale explicitly if you do SVD and get the solution. So let's go to wrong measurements. Sometimes you have wrong measurements. So I guess some of you did some physics experiments when you were in intermediate or high school. So this is just a simple example of measuring Young's modulus. So you apply stress and measure strain and get the Young's modulus, right? Stress by strain. So this often happened like when we're measuring so you measure 5 times and you get the least square solution by averaging. But then sometimes one of the measurements is completely wrong because somebody put some different weight and said this is the right weight. So that happens often, right? So those are wrong measurements. So the thing is, it affects your estimate of the solution drastically compared to just simple noise that we saw in data points. For example, you have this data point on the top. So this data point in the top, and you have this, you're trying to fit these data points with the line. So you do linear least squares, and you get this. So the problem is this happens a lot because in real settings, you always have wrong measurements. Your algorithm doesn't work perfectly. So how do you solve this? There's a very simple solution. So you just remove this point, right? And you have good solution. Will you have good solution if you remove this point? So how do you remove this point? If you do linear least squares, then your solution will be already off. And you might not just have one. You might have, let's say, 10 such points. So your solution could be anywhere. So this is also a way to get optimized for a solution. But by measuring what we call consensus. So this is what we'll talk about. So these wrong measurements are called outliers. And especially in 3D vision, in computer vision, they happen often because you are trying to match points, corresponding points between images, and you will see that often they are wrong. They're completely off, right? Yeah, I already told you the answer here. So you want to solve that problem by removing the wrong measurements, the wrong matches. So how do you do that? So we call it random sampling and consensus. So this is a very important work in 3D vision, and all of the 3D vision methods, most of them rely on this. So what you do is you randomly sample first, and then you check the consensus. So randomly sampling means you want to fit a line here with the minimum number of points. How many points do you need to fit this line? 2, right? So just select any random 2 points, and then you draw a line. Let's say you draw this line, and you have this line. Now you check the consensus. So what does it mean by checking consensus? It means that you're measuring how many of your points agree with your line. So the line that agrees with most of the points is a solution.
The point should lie on the line or within a margin?
So within a margin of this epsilon, because you know that the points are noisy, so they will never lie on. Even though they are correct, they cannot be perfect, so they will not lie on exactly the line. But within some error, small error. So we're done. We removed the bad point and solved the problem. So this is just a summary. So how many points do you take for a given problem? It depends on how many points you need to solve to fit a model. For example, if you're fitting a plane, how many points do you need? 3 points, right? What about for the fundamental metrics? How many points do you need to fit a model? How many variables are there? 9. So you have 9 points. Sorry, 9 variables. So do you need 9 points? How many? Yeah, you have one more constraint, right? You have that you can fix the norm of the vector to be 1. So it means that you need 8 points to fit this model. So for fundamental matrix fitting, you need 8 points to fit the linear model, and then you can evaluate the residuals, and then compute inliers and outliers. So how much you put this this epsilon thing? So it depends on your data and your problem. So you have to see what threshold you want to put to reject outliers. So we'll go back to real optimization where you have a cost function and you want to minimize that. So in linear regression, this is the cost function, right? AW minus Y. And this 2 thing means this is an L2 norm. We already, I guess, talked about this yesterday a bit. And we want to minimize for the parameters W. So this is the example from before. So now everyone has seen this curve, right? For optimization. So we want to go to now gradient descent. What is gradient descent and what does it even mean? So the first thing is gradient derivatives. So what does it? So you have, let's say you have a function f equal to fx. Can you guess what the function is? It looks like a parabola, right? So it's f equals y equals to x squared. So here you have a y-axis. So this is there is x-axis, and you take a point, and you take the derivative, which is the slope of this tangent line at this point. So what does it mean? It means that, so it gives you the increase in function per unit change in your variable, your parameter, right? So how much y is increasing per unit change in x in that small region. So can you guess what's the direction of this derivative? Who said upward? Like this. So what does it mean by direction of derivative? Is it a vector? It's not a vector, right? Here, if you do derivatives of y equal to x squared, you have 2x. So it's a single component. So its direction, if there is single component, then direction is positive or negative, right? So the gradient has here direction positive or negative. So here it has positive, yes. So positive gradient means that if you go further in x, your function is going to increase. If you go in positive x, your function is going to increase, right? So that's not what we want, is it? We're talking about minimizing this function. So this is the direction of the derivative here. Now, in gradient descent, we follow the opposite direction because we know that's where the function is going to decrease. So your parameter here is x. So you want to go in this direction of x, your input variables, where the function is decreasing. So what happens if you go in the negative of the direction of the gradient? So here is the same, right, as before. So this is increasing, and this is decreasing, and you follow this direction, and you get, perhaps, you will get this solution. Here, if you minimize, you will go this direction, so just as small thing, minimization and maximization. So usually we always talk about minimizing a function, but oftentimes you have maximization problem. And for example, here you might want to get this point because the other points doesn't seem to be relevant, and you would maximize the function. And you can still use gradient descent. Here you would go towards the direction of the gradient. So how do you express gradient descent? So what you're doing is you're assuming that the function is linear at that point. Then your solution, your next point will be a linear function, right? You want to go down linearly. So that's why you do, let's say you have, you want to get this next point. The better solution is previous solution in the negative direction of the derivative. And lambda here is the step size because you want to control how much you jump at each time. If you jump too much, you might get away from the solution. So you want to fix that. So there is one more thing you might notice. What's the difference between this point and this point? So the magnitude of the gradient here is very high, right? Yeah. And what about here? So you'll also notice one more thing. Can you guess? That this is close to the solution, and this is further from the solution. So this happens often in problems where when you get to the solution, when you're arriving at the solution, the gradients are very small. And when you are further away, your gradients are high. So it means that if your gradient is high, you might want to jump more. You can afford to jump more towards the solution and not go outside, right? The same, so if you have low gradient, then it means you have to be careful not to jump too much from the solution, from the initial point. So that's why you do something like this. So you scale with the magnitude of the gradient, because this is your jump size, how much you jump from your initial solution towards the optimal solution. So if your gradient is high, means you can jump more. So this is the same thing. So here the function is y equal to x squared, and you have this derivative. So what is the direction dy by dx times magnitude? And this is just a gradient, right? The direction, we don't need to. So let's look at this video. So here you will see that there is one valley here. So this is another valley here. And this is the start of this is your initial solution where you start optimizing from. So you'll notice a few things. So depending on where you start, you will end up at different valleys. For example, if you start this side, you end up here. And as you see, as you go towards the solution, it's slowing down. So here as well, because it's almost flat here, the optimization is very slow. So there are two things here. So first thing is that your behavior depends where you start optimization from. So you need an initial solution to start with. So the better your solution, initial solution, more likely you'll end up in good solution. And the other thing is your function also dictates how the solution, whether you will have good solution or not. For example, if you have a function like something like this with a very big valley, it will take forever for this gradient descent to converge to a solution, right? So more complicated stuff, because we never have a single variable, right? We always have multiple variables. And input, you could have, in a deep network, you could have image as input or features as input, which would be I don't know, 1,000, 2,000, 10,000 dimensions. And your model predicts some output. Let's say that the output is scalar. You have y. So you want to derive gradient descent here. The derivations are always fun, right? So let's go. So here we usually define in place of gradient, we define a Jacobian. So it's a matrix usually. So for this case, since the output is only one dimensional, it's a row vector with x1 here, x2 here, x3 here, and so on. The derivatives as a row vector. And that's called the Jacobian matrix. So here, if you want to do gradient descent, we need to update each variable with the gradient of that variable. Right? So this is the equation. There's nothing new. Everything is the same as before. It's just instead of only one input variable, now we have many variables to update. And same, we keep the step size the same for every variable. So that's also simple. So now we don't need to say direction and magnitude all the time because your derivative will have direction and magnitude. So you just replace that with this. So if you write in terms of a single vector, you will have lambda times this thing, right? The derivatives. And this you can express as, this is just a transpose of the Jacobian. This vector is the transpose of the Jacobian. So I'm writing x star as the next solution and x naught as the initial solution. So this is the Jacobian at x naught. So you are linearizing around the initial point and doing gradient descent. So next is, I guess everything is clear here. Well, let's go to more complex things then. Now we have multiple outputs. When can this happen? Can you think of something? Why are there multiple outputs? A function can have multiple outputs, right? For example, if you take y equals to ax. Sorry? Y equal to root x. Yeah. Root of each component of the vector. Yeah, that could be a multiple output function. But linear function as well, that could be a multiple output. We did ax equal to y all the times. So you have a is a matrix which acts as a function, linear function, and gives you a vector y. But we are not considering linear functions as such because they have a very simple solution. You can optimize very easily in closed form. So now we have y equal to fx. This is a vector. So what do you minimize here? What would you minimize here? So you could minimize each component of y. Then it will be the same as what we did here, right? Except that for each component of y, you have a different gradient descent. But generally, when what we do is we predict a vector, and we want to minimize the residual, the error in the vector prediction. And this, you can do it by minimizing the norm of the vector, right? So if y is your error vector, so you're predicting many things, and each of them has some error. So what you do in the end is you can measure the error in y, and you can optimize the model by reducing y as much as possible. So this is what we generally do in most of the optimizations. In a lot of these optimizations, we minimize the vector norm. So it could be residuals and differences between predictions and training labels and so on. So you will see later that how we optimize in classification. You have a specific way of optimizing this, but that's not what we're talking about here. This is normal vector prediction. For example, you might be predicting, let's say, height and weight of a person from their face. It's not a very good example, but that could be one problem. So what we do is we minimize the square of the norm. So this it can be written as y transpose y. Is everyone okay with this? So this is the dot product, right? Yeah, the dot product will give you the norm. And next, so what we have to do now is, let's apply gradient descent here. So we need to derive this function. This is the function with respect to your input. Sorry, with respect to your model parameters. So x is the model parameters here. Sorry, this is not the input. So x is, and your model depends on different x, right? So I was putting theta in before and I replaced that. So if you see theta, don't get confused. So it's x here. So now what we have to do is we have to derive your residual with respect to your model parameters, x, and get the derivatives. So this is the derivative with respect to x, and you see you have a Jacobian in the end. So Jacobian is just a row vector, something like this. So it's a row vector if you have only one output. But now your f is, again, a vector, right? So you have multiple rows, each row for each component of the function. So if you want to, so we can summarize now. If you want to minimize a single scalar y, like we did before, then you have this x equal to x minus lambda j. So if you want to minimize the vector norm, your equations will be something like this. So what is important here is you just have to remember that oftentimes we minimize the norm of the vector and not the vector components itself. And then your equations might look for you like very odd but that's because we are minimizing the vector norm. So few things here. We can talk about the convergence. So convergence is just when you find how you find the minimum or the optimal value. And it depends on many things, right? So what's the first thing it depends on? Can you guess? Just say, anything that comes to your mind. What was that? Amount of step, right? Yeah. So there are actually tons of things. So you have amount of step. So you have initial point of your model parameters, x naught. Then you have your surface, which is your function, right? It depends on fx. So also, yeah, the gradient of fx, which again depends on fx. So you have to consider all these things, and the first thing again is that some of the functions are good to optimize, and some of these functions are not good for optimizing. For example, let's say you have a function like this. And you start here. Can you guess what will happen? There is no local minimum here, by the way. This is straight line. This is a straight line, okay? This is a horizontal straight line. Yeah. Oh, okay. Yeah, I will put it. So you have this, and your function looks like so this is not going, there is no local minimum. Yeah. Yeah, it will get stuck right over here, right? Also, if this gradient is very low, even if this is not straight line, it will take forever to go from here towards here, because the gradient magnitude is very low. And when you set, so you have to set your step size really, really high to be able to go there. So the same, for example, if you have something like this, wave, water falling, then if you start from here, it will get stuck here. You follow the gradient, it goes here. Now the gradient is 0. So these are a few things you have to consider when you're optimizing. So if your function is not good, what do? You give up, right? No? So sometimes you can change your function, or you can change your method to optimize. So the answer is, so what happens if your gradient magnitude is very high? So let's say we didn't even do the first question right. You have something like this. So what could happen is you do gradient descent, but then you might jump too far because your gradients are too high. And I'm showing this in 1D, right? But for example, in real cases, you have like millions of parameters, and you're doing gradient descent, and you have a high gradient. So this could certainly lead you to somewhere very bad, a bad solution. So that's why in all of these deep networks, when you train your model in deep networks, sometimes you clip your gradients. If you have played with deep networks already, the reason you clip your gradients is because you could jump too much, too high. So if your gradients are too high, so you just clip the gradient magnitude so that you don't jump so far. So another thing that is relevant, we'll go to the next type of optimization. So there was one problem, right? When we're solving this y equal to x square problem, where you had this thing, and when you're approaching the solution, the method would slow down considerably. Like here, it would take forever to solve. So there are other methods which try to address that. So one of them is called Gauss Newton. So what you assume is the reason it's getting stuck is because you're assuming that the function is linear around that point, and your line is almost horizontal. So it's thinking it's already at minimum, so you don't need to move too much in the line. Because if the line is almost horizontal, the gradient, then it would think that it's already at minimum, right? So the one way to solve is if you approximate your cost function to be second degree, a second degree curve, then there at that point, instead of assuming a line, it will just assume the curve. So for y equal to x squared, it's already second degree, right? So you will immediately get a solution. So that's the motivation. So in Gauss Newton, again, you optimize not the vector component, but the vector norm square. So function to be optimized is not f of x, but f of x norm squared. So y norm squared. And what you do is you linearize y, meaning that you put this to be 0. So again, y are residual functions. Just the time. So if you put this at 0, you can rewrite this equation, right? Using the Jacobian like before. So you get y equals to y naught plus Jacobian times x minus x naught. So in terms of so what do you have to minimize? You have to minimize y, right? Norm of y. here we said we would minimize norm of fx squared. So that's norm of y. So we can just take the right-hand side now, right? So you can minimize this. What is this? Can you see? So what we're trying to find is x star minus x naught. And this is your Jacobian at x naught, and this is your function value at x naught. So these are constants, right? For this task, this is constant. This is a constant matrix. This is a constant vector. What do you see? Do you notice something nice? So this is a linear problem, right? You're optimizing for y plus j times x, minimizing for x. So what we're arriving at is, at each point when we try to find the next point of this for optimization, we have a linear least square problem. So every point we assume that the function f of x is linear, and hence the cost function f of x squared is second degree curve. So you can solve this with the pseudo inverse, right? This is the pseudo inverse. Do you see this pseudo inverse? So what problems can this method have? All right. We already discussed problems of gradient descent. So in a way, does it solve gradient descent problem? For the example we showed before, it does, right? Because if you are here, if this is your y norm square, and then, so this is a solution. This is a solution you want. If you're here, it will directly jump here, because it will try to fit a curve and get to the minimum of this curve directly. So if you have something like this, here, it will fit a curve. So this is your function. And what it will do is, it will fit a curve, second order curve around here, and directly jump to the minimum of this curve. So that's what's happening. So the problem is that sometimes your functions are so, what we call non-convex. Something like this, right? Extremely non-convex. Then what will happen? So your gradient at some points might be very high. So it will just assume a curve which is like this. So for example, this was the curve function you wanted to optimize, then because it's very steep, then it will just go somewhere like this. So very far. And then it can keep on oscillating in some cases. So this is another problem of, is one problem of Gauss Newton. The other problem is quite straightforward. I guess we should do a break now, half an hour. So we'll carry on until the optimization we do in deep networks. And in the next part, we will do the image processing and computer vision. After convergence, right? So but then there are problems where it can oscillate because the function is too not good to optimize. Whereas even in cases where gradient descent would converge, like the example I showed, where it's like this kind of, sorry. Yeah. This kind of functions where even gradient descent would normally converge, Gauss Newton can fail. Then there's another thing here, right? Because so what we are doing, so this is gradient descent Gauss Newton. Yeah, here what we're doing is solving ax plus b equal to 0, or ax equal to minus b. So we discussed when we can solve this problem. This is a linear least square problem, right? So when can we solve this to get the best solution? There were cases like we summarized when we can solve the equations. Does anyone remember the summary? There are different cases. When you have more number of equations, when you have less number of equations, and this thing, right? When you have less number of equations than the unknowns, you cannot solve this. So the equation here is, you see that the equivalent of A is the Jacobian. So if the Jacobian has less columns than, less rows than columns, then you cannot do Gauss Newton. So you have J equal to function 1, derivative of function 2, second component, third component, and so on. So your function or your vector residual should be long enough so that you can invert this matrix. So you can have pseudo-inverse, right? So this is something you have to remember. So what do you do when you don't have this, when this is not invertible? So that's the next part. So we call this method, so this is Levenberg Marquadt method. So it's a very simple change, right? Your equations are almost similar. So instead of JTJ, which is approximating the Hessian there, we add a little bit of what we call damping. So we change this a little bit so that even in all cases this will be invertible, always. So what's happening here is that if you remove this JTJ from here, what do you get? X naught minus JT lambda, so I is just I, right? So JT Y naught. Do you remember this? Let me go back so you remember. Here. This is gradient descent. Right? So what it means is, sorry, here, yeah. So what it means is you're approximating, you're interpolating, your method is somewhere between Gauss Newton and gradient descent. So you're trying to get the best of both, to get a faster solution and also not to oscillate. So how do you control it? You control with lambda. So if lambda is high, it means you're going towards gradient descent. Sorry, no, the opposite. So lambda is getting inverted. So if lambda is high, you're going towards Gauss Newton. So what you do is if at a certain point you find that the function oscillates, how do you know if a function oscillates? You just check with the previous value, right? So you get new value of parameters x star, and you have your old parameters x naught. So you simply check x star is less than fx naught. This is what you're looking for when you're optimizing, you're minimizing. So if you have this condition, then no need to worry, you carry on. But if it fails, then you have to decrease lambda. So usually decrease by 10, factor of 10 or something. So you're saying that Gauss Newton is not good there. Go towards gradient descent. So this difference is somewhat an interpolation between the update you get from Gauss Newton and the update you get from the gradient descent. And so if you have any cost function which is a residual vector and you want to minimize it, it's a normal residual vector, then this is usually your first method of choice. So and any cost function. But deep learning is special, so we don't use this in deep learning. Can you guess why? Yeah, so let's go to why isn't it used in deep learning? Let's go to AlexNet. So this is just a simple, this is not a big network by any measure, right? So the first, one of the first deep networks that was using convolutional neural network in 2012. So it has 60 million parameters, which is the size of X, right? The X is a 60 million long vector. So imagine optimizing that. With gradient descent, you have a Jacobian that's 60 million. That's still okay. But what if you were doing Gauss Newton or Levenberg Marquadt? You would have to get this, right? So what's the size? 60 million times 60 million. You need a big computer, very big, like this room. But there is also another reason you don't use use this in deep learning. The thing is that Gauss Newton is very bad when your function is very non-convex. So very extremely non-convex functions, you don't want to use Gauss Newton at all. Just do gradient descent. So, and that's another reason so you could switch to Levenberg Marquadt, but still it is a form of, there is Gauss Newton there. So usually, so this is again continuously changing, right? The state of the art, the results. So people are investigating second order methods of optimization, but so far it still seems to be dubious that whether it's helpful. So in deep learning, we always use still gradient descent. So next is stochastic gradient descent. So this is a very, I don't think this example is better than what we had yesterday or before. So let's say 50 people, each person is represented by height, weight, gender, and you want to predict their calories, input, calories spent, let's say, yeah. And this is your deep network, right? So only 50 examples. So what you do, this is a training data set, and you have labels. The label is a real value here, like 2,000, 3,000, or whatever. So when you train a model, what you do is you check each of these 50 people, each of these 50 samples. For each of these 50 samples, you compute the Jacobian because for each sample you have a residual, right? Y, which is a single vector here, single component. And for each sample, you will have a Jacobian. So to update the model parameters, what you have to do in gradient descent, you sum all the Jacobians, or you take the mean or whatever, right? Mean and sum there. Only difference is the scale. So you have to evaluate all the 50 samples. So imagine training a deep network where you have, let's say, 1 million images. So if you want to update once, you would have to evaluate on 1 million images every single time if you do gradient descent. And that's going to take a while. So you don't usually use gradient descent as such in networks. So what you do is, gradient descent evaluates all samples for each update. So what could you do? What else could you do? Yeah, so you could pick only few or one randomly, right? So you only choose one sample at each time randomly. And let's say you just I is the random index of the sample, and you choose the Jacobian of a random sample each time. Then you update using that sample only, all the parameters, and then you take another sample, and before you take another sample, you shuffle again the data index. So you choose I randomly. Then you can get another update, and so on. So you don't evaluate all the samples every time, but you do. That's why it's called stochastic. You randomly choose one. And this is a lot faster, right? I mean, 1 million compared to 1. So then you train your network this way. So it's very, very simple idea. There is nothing fancy. Just choose one sample. So objective functions, we talked about optimization, we talked about methods, but how do you, what vector do you want to optimize? Or what cost function do you want to optimize? So usually it can be it can be differently posed. So you will see later in learning that if it's a classification, you design a loss differently. If it's a, let's say, prediction of a real value, like, for example, here, calories, then you do it differently. For example, for this case, you have label of calories, so you just want to minimize the error, the square error between the predicted and the real calories. So, but often they are vectors. So if your output is a vector, or your prediction output is a vector, and your labels are also vector, then you do, again, you minimize the norm squared. So we'll go to one example in the next class of computer vision, where we are doing again 3D reconstruction from multiple images. For now, we will not talk about that. So let's go to distance functions. So again, back to errors or residuals. What are errors or what are residuals? So what you're doing in residuals is you're measuring the distance of your prediction to the labels or to what you want. So that's residuals are you're measuring distances, right? So you can measure distances in how do you measure distances between vectors? Norm, yeah. So that's where norm comes. Vector norm is it gives you what's the size of the magnitude of the vector in different sense. So there's L1 norm, there's L2 norm. So these two norms are very, very important. Can anyone come to the board and give the definition? L1 norm. You can pick your friend, right? Like point at your friend. Any volunteer? Come on, we have more interesting things to learn. Let's get over with. Nobody? It's too simple, right? All right. So L1 norm is just a sum of the absolute values of the components. So does anyone have any idea when you want to optimize L1 norm and when you want to optimize L2 norm? So this is the example we will see next time, in the next class. Did you learn about covariances? Not covariances. Okay, so this is just a intuition about, we talked about L1 norm, L2 norm as distance functions, but there are other distance functions other than L1 norm and L2 norm. One of them is called the Mahalanobis distance. So here you have a cluster. Let's say this is a 3D cluster. There are two spheres, and there's a new object, new point, and you want to put this new point in one of these clusters, right? Let's say your cluster first, your point is here. Your new point is here, how do you know, when you do k-means, how do you decide which cluster it is? Yeah, so you check the centroid, right? Here, and you measure distances. The one which is closer, it goes to that cluster. But I mean, just looking at the figure, you will see that there is some problem there, right? I mean, where would you put normally this? You normally would want to put here, in this cluster, not in this cluster, because it looks like it's far from this cluster in some sense. And this is not in the sense of centroid. The centroid is still here. So how is it far? So this is what Maloney's distance measures. So intuitively, this is looking at not just the centroid, but how the points are varying around. And you consider not just the centroid, but also how the points are varying to define the distance from these two clusters. So here, what you do is you first define something called the covariance matrix. So for each input, for each point, what you do for a cluster, what you do is you measure the distance from the centroid. Point to the centroid, point to the centroid. And you sum them up. So you multiply by its transpose and sum them up. So what happens is for this cluster, this distance becomes high. Do you agree? Or maybe not. So especially because of these points around, which are very far, this distance will be high. So the covariance of this cluster will be high, meaning that it has more variance inside. And for this, it will be lower, right? So Maloney's distance is defined as, so for distance between this cluster and this point, you define as your point, new point, this x is the new point, minus the mean, transpose, and the inverse of covariance, and x minus mu. So don't worry too much about the other things. So this is just the distance, right? This is normal Euclidean distance, x minus mu. Here, it's, but if there were no c, it would be normal Euclidean distance. So c changing this distance differently, it's scaling the distance differently according to what is the covariance. So if the covariance is high, what happens? So c will be very low, right? So it will scale the distance, the Euclidean distance, to very small value. So meaning that if a point will have lower distance with a cluster that has high covariance, that is outward, right? So this is the way we define Maloney's distance. And this is quite useful when you're measuring distances in probability distributions and like clusters and all these things. And you might want to use it it's very useful in many cases. So next is convexity. So we have some time. We'll not talk about convexity in detail, but I will just start with like some intuition and some basic basic principles of convex optimization. So maybe many of you have heard this term, convex and convex functions, convexity, and all these things. How many of you have heard this? Okay, very few. So maybe it's not that important. So we talked about what kind of function we want to optimize. Sometimes the function is not good to optimize, and sometimes the function is good to optimize. How do you define if a function is good to optimize or not good to optimize? First guess. When do you say function is not good to optimize? Can you?
It has a minima or maximum.
Sorry?
It has a minima or maximum.
It has, yeah, like it could have multiple minima, right? And you don't know which minimum you end up with when you optimize. For example, like, so if you start here, sorry, I need to put it over there. So we're saying that if the function is convex, then if the function is not good to optimize, then you have it might have multiple minimas, and you might get stuck in what you call the local minimum, because let's say this is this is clearly the best minimum among here, but if you optimize from somewhere here, you'll never reach there. Right? So you'll never have a good solution if you optimize this kind of functions. This is a problem in many functions and in many problems. Your functions are not, that good to optimize. So there are other kinds of functions which are good to optimize, which have shape somewhat like this, for example. If you see this, it has only one minimum, right? It's y equals to x squared. It has only one minimum. So if you do gradient descent, then you're guaranteed that you will get to the solution. It has one more other property. So this function has this property that if you dissect this function with a line, or if this function is not one-dimensional but two-dimensional, then with a plane or more dimension than hyperplane, then everything between these two endpoints, function values between these two endpoints will be lower than the line or hyperplane. So in line, it's very easy, right? You see, like, the function value here is this. It's lower than the value at the line. Similarly here, it's so if you make any segment even here, the function value will be always lower than the line. So this is what you call when your shape is convex. You have this property. Even in 3D, you can consider the shape is convex. Then you cross it. Then you have this property that the function will be convex. And these are called convex functions. The nice thing is that you have very efficient ways to optimize it. So if you come up with a function like, let's say, y square, if you want to optimize with respect to y, then it's a convex function. So you'll likely more get to the best minimum. So these are things. We will not go into detail of this convex functions. Maybe, if you have questions, if you're interested, we can discuss. So that's all for, I guess I'm a bit early for this, for optimizations. There are few more things in. I think when I was writing SVD, somebody told me I was writing in the board like A V, A equal to V or something, right? So that's not true. This is AV equal to U sigma. Somebody told me I was writing equal to here. So don't get confused. There is no equal to here. So I can also tell you more about the lab session. There is a lot of work, work in the lab session today. So first thing is, but still we will not do any particular thing in optimization because it's still, that could be even more time consuming. But you can try Levenberg Marquadt by yourself on some problem you want, if you want to try. What we'll do in today's lab session is we will reconstruct 3D using 3 images. And then, so there are like multiple steps to do for that. And you will have like 1 hour or 2 hours maybe for that. I think it should be, 2 hours should be enough. And then you'll have like you'll have the lab session of the other part, image processing and all these things as well. So since I am finishing early, if you have any questions, I think it's a good time.
Yes. In your last class, you discussed some intuitions about the singular value decomposition.
Yes.
I think it would be great if you could explain more about that.
You mean like a derivation of how you get it?
Not really. The intuition behind SVD.
The intuition.
That equation, AV equal to U sigma.
Yes. Okay. So there are many ways you can look at SVD, but for me, I found the best way to describe SVD decomposition is that it's a decomposition of the transformation. So your matrix A is a transformation; it's a function. So what does a function do? A linear function does a few things. It can rotate. Like it can rotate the vector. It can also shear the vector. Shear the vector means that it can scale the vectors differently, different components differently, and different vectors differently. And then it can rotate again. So if with a different rotation. So let's do it this way. R2, sorry, this is the first rotation, and this is the second rotation. So any transformation matrix is a product of is a transformation of is a rotation followed by scaling and some other rotation. So this is what we are trying to do in this is the actual decomposition of any given matrix. And the other way is to see is that if you take this one, so let's just write SVD here. By the way, there is a thing about this matrix. If you do SVD in Python, it returns you V transpose, not V. It will give you back V transpose and not V. So that's why you have to be careful when you take, so instead of taking the last column as solution, you have to take the last row as the solution. So that's the Python thing. Normally, in other languages, it's different. So here, the other thing is your input dimension of X is always a, so if R has a, if it's M by N matrix, then it will have a, the input can be any vector in the vector space of M dimension, right? The input can be any vector in the M dimension, so which is called Rm. So you can always describe Rm. You can span Rm with some orthogonal vectors. So any vector is a linear combination of these orthogonal vectors in Rm. So you'll have some orthogonal vectors. Let's say A1, A2, AN. So these orthogonal vectors, so we want to see what kind of orthogonal vectors will be transformed into another set of orthogonal vectors. So the input can have different sets of orthogonal vectors. And not all sets of orthogonal vectors will get transformed as orthogonal vectors. So each matrix will have only one set of orthogonal vectors that will get transformed as orthogonal vectors in the output space. So that's what this is. Like when you do A times V, you get U sigma. So U sigma is another set of orthogonal vectors. The only difference is that now it's being scaled by sigma, right? And also, since sigma may not be a square matrix, some of these U's will vanish. Some of these orthogonal vectors will vanish as well. So this will give you because sigma is making some orthogonal vectors vanish, it means that some of these vectors of V are in the kernel of A. So that's another way to look at it. And you can also look at it as so if you have data, your data points, let's say you have some data points like this. Let's say this is in R3 data points, and you do SVD. You put the data points in a matrix, and you do SVD. what it gives you is a set of orthogonal vectors where you have a maximum variance, right? So that's another way to look at it. It's a very, very useful decomposition, and it's not just to solve Ax equal to 0 that you will need SVD. You might have different applications.
Any other questions? Okay.
Yesterday we learned about L1 and L2 regularization, and in that I personally just learned that L1 is for taking the coefficient to 0 of input parameters which are not important to output, right? And L2 heavily penalizes different wrong values. But you just talked earlier about using for sparse and dense metric as output. So how do we relate those two?
Sparse, yeah.
Should I repeat the question or you?
Yeah, your question was about how is it relevant in sparse matrix?
Yeah.
So as far as I know, it's because sparsity is again quite similar to what you have in the case of when one of the components are very different from the other components, and you want to make your optimization robust. When it's sparse, then only few of the values will be, some real number. All of them will be 0, right? So these few values will dictate the norm of your whole vector. And if it is wrong, if one of the values is wrong, then it will severely affect, right? So if you just take an example. So 0, 0, 0. Let's say there are only two values in this sparse matrix which are non-zero. The last two values. So in a way, I mean, usually sparse vectors have even more zeros. But let's say this is the sparse matrix you're talking about, and let's consider another dense or not sparse vector. 5, 6, 10, 3, 50, right? So here to see why we use L1, what you can do as an exercise is, here remove 50 and put another value and take L2 norm. And do the same here. Remove 32, put another value. Let's put 0 here, and let's put 0 here. What is the change in norm? So in sparse matrix, if your value changes, it affects a lot more. So you need more robustness to make sure that wrong values are not affecting the whole optimization.
So can I add something over here? Maybe I'll try to explain. I mean,
yes.
If I'm wrong, correct me, okay? So in this L1 num and L2 num, so we append one regularizer in the objective functions, right? So that one will be W1, and another num will be W2, right? So then we minimize this loss function. So here can be another loss function, parameterized with W and X.
But were you talking about the loss function L1, or were you talking about the regularizer?
Or something else.
L1.
Yeah. So then if you differentiate it, so this will be either 0 or 1. This is something W1, W2, and if you differentiate with respect to 1, W, So it will be 0 or 1, it will constant. But our aim is we are minimizing it, right? So how can we minimize it? Is if we make many of them 0, then it get minimized, right? So then it basically imposes sparsity. And here we are minimizing the norm. It means, so if you, this is something like, correct me Azad, okay?
No,
Yeah.
that's
And
all
W2, let's say that
square.
is square, right? So if you differentiate it, so it is will be in terms of constant time W1, constant time W2. So basically, if you want to minimize it, the value of W should be small. So this imposes that, this L2 norm imposes that the modal parameters are small, close to normal distribution, right? Then the advantage of L2 norm is like if there are some outliers, then it penalizes. It does assign very high weight for some
for L1.
noise.
For L1.
L2 and L1 basically it imposes sparsity. It wants to make the modal parameters
Okay.
0, more 0, because we are minimizing this form, right? So if it is a constant sum, if it's 0, 1, 0, 1, 0, 1, so then if you want to minimize it, then if you make many hyperparameters, the vectors 0, then it will be minimum, right?
Hmm.
So this is how it imposes the sparsity. And here it imposes that the modal parameters should be small. The advantage is that, yeah, as I said before, if there are some outlier features and then it assigns less value, and our model will be robust to this kind of outliers. So this is my understanding. Maybe you can
Yeah.
add more on it.
Well, yeah, that's. Yeah.
Any other questions? Oh, yeah.
Slide easier, and we can switch to this as well. Using standard L1 or L2. So the idea is L2 might strings all of
The
them.
solid one.
Okay. I've been volunteered to.
I had one question. Like
Yeah. I'll use
Maybe I don't need this.
I've heard about like people talking about saddle points when they talk about optimization as well.
Yes.
So I just wanted to know like what they are and are they also solvable by the Gauss Newton method or like is that a different thing? Or
Yeah,
saddle-
saddle points are basically
Thank-
where you have this. So yeah, I guess I sort of forgot to talk about this. When you have the optimum of a function, right? It's when your gradient is 0, then you might have an optimum there. If the gradient is, if your gradient is 0 and if it's just flat, and like the function is not changing, then that's a saddle point. And there, I mean, if you use Gauss Newton, it will help you avoid that because it can jump. So for example, I was giving the same example before, so I will draw it again. So in gradient descent, I was giving this example. So this is again not a local minimum, right? This is a saddle point. And you have this kind of function. And you have the minimum here. So if you do gradient descent, then it will stay here somewhere. But if you do Gauss Newton, it will approximate, if it's at here, it will approximate this curve and create a second degree curve by approximating the curve here. And it will directly jump to the minimum of this curve. So it will go somewhere here. So from now on, it might get, again, derivatives. And then it can proceed. So that's why in Levenberg Marquadt, if the optimization is slow, then you can switch to Gauss Newton as well.
I just wanted to know, like, is the saddle point same as this?
Yeah, yes, yes, the same thing, yes.